Hello, I'm Dr. Andy Hales at the University of Mississippi, and in this video we're going to look at how to do post-hoc tests after you've run a one-way ANOVA in R. So for starters, you'll recall from the last video that we can use this method here using the AOV_EZ function to run a one-way ANOVA, and when we do that, we get a new object called myANOVA. And we saw earlier that we can interpret the F value, the effect size, the P value here is very small, so there's probably something going on. However, you are aware that a one-way ANOVA, an omnibus test, doesn't tell you where those differences actually are. And if we didn't plan out ahead of time which planned contrast we were going to run, then the tool for the job here would be a post-hoc test. So we're going to do pairwise comparisons, meaning we're going to compare every group to every other group. However, we know that if we run a bunch of tests like that, it's going to increase the family-wise error rate. Eventually, something's going to be significant just by chance alone, so we have to control for that. Now, to run this, for starters, what I'm going to do is a pairwise comparison where we don't control the family-wise error rate. I'm going to do that just to establish a baseline so we can see the difference from when we do control the family-wise error rate. You understand in real life we would never recklessly just do a bunch of t-tests. That would be a recipe for false positives. But let's see what it would look like if we were maniacs who did that. So for starters, we're going to use EM means, and we give it the name of the ANOVA object we just created. And we tell it we want to do pairwise comparisons using the condition as our independent variable. And here we're not going to perform any adjustments just to see what it would look like if we were to be crazy and do that. So here's our output. For starters, it reminds us the mean of each condition. We already did this earlier with descriptives. Conveniently, it also includes a 95% confidence interval around each particular mean, which can potentially be useful. But more to the point, down here under contrast is where we see each of the pairwise contrasts. So to interpret this, the first row is saying the difference between the control and inclusion group is a difference of 0.64 units on whatever scale we're using. And here it's a 1 to 7 Likert scale, and that matches what we see on the graph. The inclusion group is 0.64 Likert scale points higher than the control group over here. Is that a significant difference? Well, with the huge grain of salt that we haven't controlled for multiple comparisons here, we have a t-value and our p-value is not significant, even using this crazy, very brash approach. So those two probably not different. However, we also have these other pairwise comparisons, control compared to phubbing. That's 2.5 Likert scale points apart. We have a stronger t ratio and a very significant p-value. Grain of salt, though, we haven't controlled for multiple comparisons. So the last comparison here is the inclusion condition compared to the phubbing condition. Those are 3 Likert scale points apart, and the t ratio is stronger. P-values down here, uncontrolled. Cool. So that's how you would do a pairwise comparison in general. But of course, in real life, if we're doing this, we're going to want to control the family-wise error rate, and we do that by adding an adjustment. And here we can tell it to use the Tukey post-hoc adjustment. And if we run this, we get the same comparisons. The difference is that this time, these p-values have been adjusted to be more conservative to account for the fact that we're doing 3 different comparisons here. So whereas before, the p-value comparing the control group and the included group was a p-value of 0.14, here you can see it's a much more conservative p-value of 0.304. Okay, so it's not significant in either case, but it's easy for you to see here how that could, in fact, make a very big difference. Now, it turns out that the other 2 differences we looked at, control versus phubbing and inclusion versus phubbing, even after applying the Tukey post-hoc correction, which of course we would always want to do, it still remains statistically significant. So that is reassuring if we were interested in showing that the phubbing group produces worse well-being than the other two groups. So that is how you would do a set of pairwise comparisons with a Tukey post-hoc correction. Next time we'll look at how to test specific planned contrasts.